Hello friends, welcome to our channel Knowledge Amplifier, and in this particular video I am going to discuss how you can perform histogram equalization without using inbuilt MATLAB functions. Okay, so for constructing the algorithm and understanding the concept of histogram equalization, which code acts in the back end of the MATLAB inbuilt function histeq, you must know one concept from information theory and coding course. That concept already I have discussed in a separate video in detail. That is, entropy becomes maximum when the probability distribution follows uniform distribution. Okay, what is entropy? Entropy is average information in message. You can check the link for detailed explanation. I am not discussing that concept again. So that entropy was with respect to communication system, with respect to transmitted message. Now you just try to think entropy with respect to image. So more entropy for an image means more information on image. Okay, more information means obviously more contrast. Okay, so what will be our aim? Our aim is histogram equalization. And why we perform histogram equalization? To increase the contrast. So in the other way we can say we have to increase the entropy of the image. And increasing entropy means, you know, from the information theory concept, that entropy becomes maximum when the probability distribution follows uniform distribution. So whatever histogram, whatever probability distribution function will be having for our image, we will try to convert that probability distribution to uniform distribution, and if we are able to achieve that, that will be our histogram equalized image. That's all. So before going to that, before converting any probability distribution whatever we will get from our image to uniform distribution, we must know some concept or recall some concept of probability theory and random process course, what we have discussed in our second year engineering course, right? So what is that? Suppose we wish to convert random variable u with respect to probability with a probability density function fu of u to another random variable v with a probability density function f(v) of v. Okay, that is, we want to map one random variable u to v. That's what we want to do. So how we can do that? That is the question. And for this purpose, we require the cumulative probability of input variable u at some value capital U to be equal to cumulative probability of the mapped variable or output variable v at some value v. Okay, I know it is difficult to understand. Let me explain. Okay, then we will again come to this sentence, which is little bit confusing appearing for this time. Consider this particular case. Suppose I am having one probability density function of one random variable u, like uniform distribution. Don't consider this Gaussian distribution or bell-shaped curve. For the time being, consider this one. Okay, that is uniformly distribution. If this is the probability density function, then what will be cumulative probability? That is nothing but integration. If we do for this uniform distribution, we will be getting ramp. Or in terms of signal processing concept also, we can say that integration of unit step is ramp, so we will be getting one ramp signal, right? And maximum value will be 1, because obviously cumulative probability will take maximum value will equal to 1. If you sum all the probability, you will be getting 1, right? Suppose we want to map this particular, understand it very carefully. Suppose we want to map this particular uniform distribution to one Gaussian distribution. Suppose the random variable is v, which is having probability density function like this. Why I am telling probability density function? Because this is continuous. If it is discrete in nature, then you can consider probability mass function. That is, wherever integration we perform, instead of integration we will be performing summation. Okay, I am discussing with respect to continuous domain because continuous domain feeling is more than discrete domain, but images act in discrete domain because images are discrete values, right? Pixels are discrete values. You can apply the same concept in discrete domain also, no problem in that. Just instead of the name probability density function, it will be probability mass function. Okay, so suppose I am having one probability density function of random variable v, which is like this kind of bell-shaped for Gaussian distribution. Okay, well-known Gaussian distribution. Now what will be the cumulative probability for this particular bell-shaped Gaussian distribution? No doubt this one. Okay, cumulative probability, it will add up, and at the end obviously it will be taking maximum value as 1. So our aim is converting this particular probability density function to this one. Now what I have written, try to understand. For the mapping from random variable u to random variable v, we require the cumulative probability of input variable u, that is this u, at some value of our random variable u to be equal to cumulative probability of the mapped variable v at some value of v. Why I have written some value of v? Why not same value of v, where we are getting cumulative probability u at that same point at for same value of v? Why we are not getting same f of v? Because you can clearly understand that if these two, if we want to convert from this probability density to this probability density, that is what I want to say, that for this particular cumulative probability at some point the value will be equal to the cumulative probability corresponding to the random variable v. Okay, see why, let me explain. Because it is starting from 0 going to 1, here also it is starting from 0 and it is going to 1. So no doubt, if we are mapping from u to v, obviously this will be satisfied that somewhere whatever values this f of u, that is this cumulative probability is taking, that same value our this particular distribution will also take, because this is also continuous from 0 to 1, this is also continuous from 0 to 1. So for some value of u, whatever cumulative probability we are getting for this f of u, that is input distribution, at some random value of v may not be same value, at some value at least we will be getting the same. Okay, that's what it is written. Okay, so this concept we can use to map from input to output distribution. Now you may think, why I have not told with respect to probability density function, why I have considered only cumulative probability? Because you can assure this statement for cumulative probability only, that if u of u, that is cumulative probability, equal to f v of v at some point, pakka, this is for sure 100%. But you cannot claim the same statement for probability density function. Why? It's very simple. Suppose you have this uniform distribution and your output distribution, where you want to map this input uniform distribution having this kind of Gaussian distribution. Now you just see the maximum height itself of the output Gaussian distribution is lower than your uniform distribution value. So nowhere, at no position, your f u of u equal to f v of v, that is input probability value, nowhere it is equal to output. Okay, so you cannot claim the same for probability density function, but you can claim the same for probability cumulative probability, because it is continuous from 0 to 1, both input and output. So obviously at some point they will be taking same value, may not be same value of u and v, but the f of u and f of v of v will be same at somewhere. So that's what I have written here. If we are mapping from u to v, f of u will be obviously equal to f of v for some value of u and v. Okay, now we want the mapping function, that is the system we want, where we will be giving the input the uniform distribution and we will be getting output the bell-shaped curve. For this particular case I am telling, in general we will be giving any input distribution, we will be getting any output distribution according to our system design. Now we require the system. Okay, how to get the system? Very simple, take inverse, right, then map. So f u of u equal to f v of v, this is obviously I am telling with respect to cumulative domain, because this is, here I am applying capital F. So v will be equal to f v inverse f u of u. Okay, this is very important, v equal to f v inverse f u of u. So what it signifies, what is the meaning, what is the significance of this particular expression? Try to understand. So what it says, suppose my input distribution is of random variable u and my output distribution is of random variable v. Now I want to convert or map u to v. What we'll be doing? We'll be taking the cumulative probability of my input distribution and we'll be applying inverse of the cumulative probability of our output distribution, and like that if we perform mapping operation, we will be getting our desired distribution in the output. That's all. Okay, now what is v for our case? As I have told you, to make histogram equalization or to increase the contrast of the image, we must increase the entropy, and entropy becomes maximum when the probability follows uniform distribution. That is, in this particular case, if V of V, that is the output distribution, should be uniform distribution. Okay, right? I hope up to this it is clear. Now consider V, that is output distribution, as uniform distribution. The input distribution U is not known. Okay, how we can know that? Because that is that can be any distribution, because we will be giving image, and for different image, different histogram we will be getting, right? If you have histogram of one image, if you just flip the image from left to right, you will be having same histogram. Okay, but if you are considering some other image, then you will be getting any other histogram. So histogram, that is input probability distribution, will be any shape. Okay, but our output we want for uniform distribution, to increase the contrast or to get the histogram equalization. Now let us simply calculate the cumulative probability for cumulative probability for the uniform distribution. So as you know that uniform distribution looks like this, typically 0 to b, 1 by b. So f capital F of v, that is cumulative probability integration 0 to v 1 by b dv. So we will be getting v by b, and you can put some values, that is fv of b, at b value it will be 1, and at 0 it will be 0. So we will be having the cumulative distribution like this. We can say in terms of mathematical expression like this. This is well known, right? We have already studied in probability theory and statistics random variable course. Okay, so if typically suppose b equal to 1, we will be having f equal to 0 for v less than 0 equal to v for 0 to 1, and equal to 1 for v greater than 1, right? So why I am calculating this? Because in this expression, closely observe, u is our random variable with respect to input image. So if u of u, that is cumulative probability, we can calculate, but if v inverse this we don't know. So for that I am calculating this. So now we have got f, that is cumulative distribution of uniform distribution, and that is basically our intention is fv of v equal to fu of u, right? So what is our fv of v, that is cumulative distribution for uniform distribution? That is nothing but v by b, right? Because 0 and 1, those are just two extreme case. Obviously it is v by b. Put that value, v by b equal to fu of u. Fu of u is cumulative distribution of my input image, v is our output random variable, and b is the range, okay, where it can take the possible values. So what is v? V equal to b into fu of u. This is very important. So this is our actual expression which you can put in MATLAB and get the result, and our problem will be solved. What we have to do? See, from here itself we can conclude our algorithm. First of all, we need to calculate the cumulative distribution of my input image. Then that how you can calculate, I will be telling, no need to worry. And b is what for image? Image takes, pixel values can take 0 to 255, so this range will be 0 to 255, so b will be 255. So what we will be doing, we will be mapping our each pixel intensity to 255 into the corresponding cumulative probability, and using this we can get histogram equalization. So if we write the code or algorithm stepwise, I will be having two steps. For image with discrete gray values, compute probability. First, to calculate the cumulative probability, at least we know probability, right? See here, if u of u, that is input side uniform distribution cumulative probability we need. Before calculating cumulative probability, at least requirement is getting probability. How to calculate the probability of an image? Simple. You get the histogram, that is intensity corresponding, that is number of pixels corresponding to any particular intensity. Suppose number of pixel corresponding to intensity k is nk, then the probability for that pixel having that particular intensity is nk by n, where n is total number of pixels. And how you can get total number of pixels? Very simple, number of rows multiplied by number of columns in an image will give you total number of pixels. In simple words, total number of elements present in a matrix equal to total number of pixels present in an image. So total number of elements present in a matrix is what? A number of rows into number of columns, right? So you just multiply rows and columns, you will be getting n value. Nk is what? Number of pixels with gray value rk. K is basically 0 to L minus 1, where L is 256. That is because 0 to 255 possible values, right? So using this, we can calculate the probability that a particular pixel, what is the probability of a pixel taking that particular intensity, okay? Then we will be calculating cumulative distribution, that is, as we are considering in discrete domain, we have to take summation and then multiply by 255. This multiplication of 255 is nothing but due to this B. Okay, this B is here 255 because 0 to 255 possible range, right? So that's all. If we perform this and then if we map all the pixels like this, that is whatever pixel input pixel intensity will be mapping to this particular 255 multiplied by the cumulative distribution, then our histogram equalization will be done. So here is the MATLAB code. Obviously here we have applied some statistical concept. It may look boring, but once you understand this, then the enjoy of handling images will be great. Okay, so what I have done, CLC clear all, close all, and then winding off. I am reading one image which is present in MATLAB database itself. imread tire.tif. Then subplot 3, 2, 1. imshow original image. So let me show you the original image. I hope you have already seen this popular tire picture. Okay, this one. Okay, I hope you can see car tire. And then subplot 3, 2, 2. imhist, and the title will be histogram of original image without built-in function. Okay, that is, sorry, with built-in function, because we are using imhist to get the histogram. So as you can see, the histogram looks like this, and from the histogram itself we can conclude more number of pixels are close to dark region, so image is darker, as we can clearly see. And here histogram is getting clipped, so you can apply axis tight to get the whole image. Okay, let me just write axis tight, and if I run now, I will be having my complete histogram without clipping. Okay, as you can see now, without clipping we are getting. Now we need to equalize this because this is not uniformly distributed, right? So what we will be doing? See, we are now calculating the h equal to 0, 1, 256. This is what? This is getting the count or frequency of pixels for a particular intensity, which I have already shown you while discussing the getting histogram of an image without built-in function. Okay, this is how we have done. Total number of pixels is equal to r into c, and n values from 0 to 255. If you want, you can ignore this line, no problem. And now if I do histogram equalization using MATLAB inbuilt function, that is imhist and histeq, so what we will be getting? We will be getting histogram equalized image using built-in function, that is this one. You can see that now the bins are uniformly distributed, and you can see that it is contrast is increased. Okay, but we don't want this, we want our own code. So how to write the own code? First step, calculate histogram without built-in function. So for each pixel intensity, how many frequency or what is the number of pixels present, that we need to calculate. So h equal, as this no need to explain because already I have discussed, h of x of ij plus 1 equal to h of x of ij plus 1 plus 1. And using this we will be having what? We will be having for each pixel, for each intensity, how many pixels are present. And then if we divide by total number of pixels, we will be having the probability, as I have shown you here also. That is, we are calculating this one, nk by n. Nk we have calculated using histogram, and then n. Okay, n is total number of pixels. Okay, that's what I have done here. For I equal to 1 colon 256, h of I equal to h of I by total number of pixels. Then what we have done, what we have to do, getting the cumulative distribution, that is this one. Okay, so for that I have calculated the cumulative distribution like here. Very simple. If you have studied data structure and algorithm in your programming course in your BTech level, obviously you can do simple, right? So in data structure algorithm, there is a very popular algorithm, that is prefix sum. So cumulative probability is nothing but prefix sum approach. So temp equal to h of 1 and I equal to 2 to 256, temp equal to temp plus h of I, then h of I equal to temp, end. And then the final step, that is original one, that is mapping. This is our transformation, right? So that I have written T of Rk, that is each pixel intensity Rk, whenever we will be getting that pixel intensity Rk will be mapped to this one. Okay, so what we have done here, for I equal to 1 colon R, for J equal to 1 colon C, simple matrix traversal like that, image traversal, pixel traversal, x of ij, that particular intensity will be mapping to h of x of ij plus 1, that is cumulative value whatever we are getting multiplied by 255. And why round? Because we generally take unsigned integer 8, 16 like that. So uint 8 if you take, so round values, that is pixel values, I am performing round off operation. Okay, then subplot 3, 2, 5 original image. This is the image histogram after performing histogram equalization. So title is histogram equalization using own code, and then I am plotting the histogram of the image where we have performed our own histogram equalization algorithm. Axis tight, title will be histogram equalization using own code, and then axis tight. Okay, axis tight already we have given, so no need to give here. All right, now let us run the whole code. So we'll be getting this kind of output. You can clearly see this is our original image, this is histogram of original image using built-in function. This is histogram equalization using built-in function, this is histogram equalization using built-in function, right? This is the image corresponding to histogram equalization after using built-in function, and this is without using our built-in function, and you can see how much close we have achieved. Okay, this is our original image, which is not at all very much contrastful, but here whatever we are getting output, that is having high contrast, that is we have increased the entropy, and you can see the histogram of the equalized image. Okay, this is our original image. Compared to that, our histogram is far better way uniformly distributed. Obviously we are not achieving the same like our inbuilt function, but it is, we are achieving the histogram equalization by a huge amount. You can consider this one and this one. Okay, input image and output image. So our aim is achieved, that is making our histogram or probability distribution of pixel intensities as uniform, because uniform distribution having highest entropy, and highest entropy in image means highest contrast. Okay, so this is what is the whole picture of histogram equalization using built-in function and without using built-in function. Same code will be posted in the description box. You can have a try by your own with some other images. Okay, try to understand the statistics behind this algorithm. All right, this is all for this video. If you find this video helpful, please like, share and comment. Subscribe our channel if you have not subscribed till now, and don't forget to press the bell icon to get the notification of our latest videos. Thank you for watching.